it's going to work.
You should stream on Twitch.
I should stream on Twitch. Unfortunately, I'm having enough trouble just getting this to work. It'd be a really exciting. I'm sure I would get many views if I streamed
You
on
get
Twitch.
live feedback in the B section.
Section B. Yeah.
Yeah, the B section.
Yeah. So let's get started here. How are you all doing? Did you survive homework 2?
Yeah, I think so.
It's due tonight. Oh, I thought it was due last night. Okay. Okay, then will you survive homework 2? Do you have any questions about homework 2? Yeah.
On part 1, so are we supposed to assume, like, let's say you do part 1, part A, like, and then part B, you're supposed to assume the output of part A's FST is the input of part B's FST?
You can structure it that way. You don't have to.
So let's say you didn't, then would you deal with strings that would have been dealt with by part A in part B's FST? So like, what?
You're only really concerned about strings. You're concerned about inputs to the whole thing that you put together, right?
Mm-hmm.
The whole thing that you compose in part 2, or that the combined FST. So you only need to worry about the inputs to the whole thing and the outputs of the whole thing, except in a system internal kind of way. So there's one way of doing this that is very straightforward, and that's the way that you're talking about. And in that case, you only have to worry about, you control completely what the outputs of a step are, right? You know, that's basically something that's fundamentally true about FSTs, right? They have 2 projections. Each projection is a finite state automaton defining a language. So on the output side, you could not output anything that's not part of the language defined by that finite state automaton. So you don't have to worry about other things.
So I guess like what I mean is like, let's say you add a new character in for like one of the parts, like you're gonna leave it as an output, and can I assume then later parts like I'm reading in that character like in my strings, if that makes sense? Like,
right. So if you insert a character,
yeah,
that's special character, it's not A to Z, then you're going to have to deal with that later on. It's still going to be there.
Yeah.
In other steps or elsewhere in the FST, the combined FST. But you don't have to worry about things other than that, if that makes sense.
Yeah, like as in we can assume the input and later parts make sense. It's not something that's just like completely not a name or something like
right,
that.
you have control
Yeah.
over what the input to the later parts is.
That makes sense.
You have complete control. And we're not going to test your FSTs individually, with assumptions external to those that you have for the FST as a whole. And you shouldn't assume that the inputs to the FST consist only of letters. All the symbols are letters. Case doesn't matter. So you can assume they're all lowercase or all uppercase. We don't care about case. The SoundX algorithm doesn't care about case. So you... is this recording? Yeah. Yeah.
So are you saying that since the specification is only designed for proper input, then we only need to meet the specification? So if we're given improper input, like a bunch of digits, then it doesn't matter what we output because that's not part of the specification?
Well, what will happen if you're given improper input? It just won't map to anything.
Mm-hmm. Okay.
Because it's an FST. So it's only going to consume stuff that, two projections, right? It's only going to consume stuff or produce a mapping for things that are in that first language, the language of the input side FST.
Okay.
Does that make sense? Yes.
Could you give a little bit more detail about what you expect for the explanation of how the FSTs are constructed?
So I expect a formula stated in terms of mathematical operations on FSTs. It can be very compact. It will be very compact. It doesn't need to be, you just need to make sure everything is defined and we know unambiguously what you mean. It might be good to say it in prose as well, in words.
Are we talking about the big FST or the just individual small ones?
The big FST.
Okay, so the small ones, there's no need for a formula. You just draw them, right?
You just draw them. That's the, you draw them and give the state transition table.
Yes.
And that's the state transition table is really the formal definition. But when they're drawn, it's much easier to tell whether you got it right. It's hard to interpret a state transition table. It's easy to read a state diagram. So, yes. Any other questions? Okay, let's talk about syntax. What is syntax? If you're talking about a programming language, and I like to talk about programming languages, so if you're talking about a programming language, what is the syntax of a language as opposed to other aspects of the language? Yes?
The arrangement of tokens?
Okay. So it's the arrangement of tokens. What about the arrangement of tokens?
It's like a particular correct way to arrange them such that it makes sense, whatever that means for the language.
So there are certain constraints on how you can put them together and how you can combine tokens within a language, and this is the syntax of the language. Well, human languages are not so different from that. And that's what we're going to talk about today. We're going to talk about the syntax of natural languages. Yes? Oh. Which side is that? Is that left or right? Okay. So we're asking the question, what is syntax? Well, let's answer this question by telling you what syntax isn't. And we're going to start off by saying that syntax is not morphology. Morphology is also, to some extent, about the arrangement of things, the arrangement of morphemes within words. But it's about the internal structure of words. And that's not what syntax, as applied to natural language, is really about. It's about combinations of words. Basically, how you put words together into phrases and how you put phrases together into sentences. It has another difference from morphology, and that is that morphology is often irregular. Morphology is actually full of irregularities in many languages. But syntax, while not perfectly regular, is largely regular. It's basically made up of general rules that apply across the board. On the other hand, syntax is not semantics. So these can get confused in some ways more than syntax and morphology. Semantics is about meaning. Syntax is just about structure. So if you bring the topic back to programming languages, then what is the distinction between syntax and semantics there? Who can give me an example? Yes.
I don't know if this counts, but like across a bunch of programming languages, you'll have like a for loop, and so it's
Uh-huh.
the same meaning in a bunch of different ways, but they each have
Right.
a different syntax for how.
Right, so you
actually
have-
write that.
Different meaning for a for loop, or different syntax for a for loop. You express it in different ways, a different arrangement of tokens.
Mhm.
But the meaning, the semantics, is the same. That's a good example. Yeah.
Well, if your program is syntactically correct, then it'll usually compile.
Right.
That doesn't mean it means anything, or what you want it to mean.
Right. So semantics, from a standpoint of a programming language, is what, or from a standpoint of a program, is what the program does, right? And in a sense, that's true of language as well. Semantics is about what our language does or how it interacts with the entities in the real world. It's what it means, what implications it has for things outside of language. Just as the semantics of a programming language, or of a program written in a particular programming language, is based on what the program does, what effect it has outside of the program. So you could have, just as you can have programs that are syntactically well-formed, that compile just fine, but don't do anything meaningful at all. Even so, you can have sentences that are syntactically well-formed, but are semantically anomalous, that semantically make no sense. So if you take the famous sentence that was coined by Noam Chomsky, colorless green ideas sleep furiously, and examine it, is this a sentence of English? Can you, English speakers, say this? Yeah, it's a sentence of English. What does it mean? It's self-contradictory, right? It's anomalous. It can't mean anything. You can't be both colorless and green. You can't sleep furiously. Ideas can't sleep. Except metaphorically. But this is syntactically well formed, but it's semantically anomalous. Now, it is true that there is a relationship between syntax and semantics in natural language, just like there is in programming. Particular syntactic constructions in programming, like a for loop, have particular semantics associated with them. And there are a number of linguistic theories where you basically have a representation of a sentence syntactically, and then you read off of this syntactic representation a semantic representation. So this is true in particular of CCGs, kind of categorical grammar, combinatorial categorical grammar. And we'll talk about this later on in the course. Professor Black has some expertise from the past in that area, and he will talk to you about it. Let's talk now about the subject of constituency and about the kind of phrases that exist in English. Now, I want you to pay close attention to this part of the lecture because there will be a homework. Not today, not tomorrow, but someday there will be a homework on where you will write a grammar of a fragment of English. And knowing something about English syntax will help you with this homework. So we think it's important enough that we're giving you a homework about it, and we hope you will think it's important enough that you will listen. So one way of looking at syntactic relationships is in terms of what is called constituency. To view a sentence as a collection of nested constituents. This is effectively how a parser for a programming language views a program. So constituents are things that go together, that are bound together more closely than other words in a sentence. And when they're larger than a word, we call them phrases. So you've got words combined into phrases. A kind of maximal phrase is a sentence or clause. And phrases can contain other phrases. In fact, phrases can be recursive. So you can have phrases of the same type in another phrase. So part of the definition of a phrase can be that it includes a phrase of its type. So this means that you can have very deep nested structures in the syntax of natural language sentences. One type of phrase are noun phrases. So examples of noun phrases include the elephant in the elephant arrived, it in it arrived, and so on. But they can be more complex than just a determiner. And a determiner is a word that we'll use. It's a word that linguists and NLP people use to refer to words like the and and some uses of this and that. So articles and some demonstratives we call determiners. They occur before nouns within a noun phrase and give certain information about the noun, whether it's old or new information, for example. And then we've got a pronoun here. It can be a noun phrase. We've got just a noun. It can be a noun phrase. You can also have a noun phrase that has adjectives. So the big, ugly elephant. It's got two adjectives and a determiner. That whole thing is a noun phrase. You can also put sentences inside of noun phrases. So I love to hate is a sentence. This is what is called a relative clause. So you say the elephant I love to hate arrived. This whole thing is a noun phrase. And it's got a sentence embedded inside of it. Any questions? Do you think you could identify a noun phrase? So how many noun phrases are there do you think you could identify a noun phrase? What are they? Yes.
You, and noun phrase?
You, and a noun phrase.
A noun phrase.
So we also have prepositional phrases, or PPs. That's what 3-year-olds call them. So these basically are prepositions plus a noun phrase. Like I arrived on Tuesday. So you've got the noun phrases underlined, and then the prepositional phrase that includes the noun phrase is in blue. Every prepositional phrase, no matter what, includes a noun phrase. So you can just think of it as a P plus an NP. That makes a PP. Fortunately, there's no phrase called a poo-poo. Then we have sentences or clauses. Clause is a word for a sentence that basically occurs inside of another sentence, and the whole thing is a sentence. And so in like John loves Mary, you've got a sentence. It's also a clause. Or John loves the woman he thinks is Mary. You've got a sentence inside of a sentence. Sometimes John thinks he is Mary. So he is Mary, and he thinks he is Mary. These are sentences, right? These are clauses. But they're occurring as part of a larger clause. So we have a kind of recursive structure, right? And you can keep going like this forever. You can say, I saw that she said that you tried to go to that school where they think that MIT is of no value. Anyway, you just keep embedding one sentence inside of another sentence. Yeah.
So then are sentences a proper subset of clauses? Because like he thinks is Mary
Yes.
would be a clause, but not a sentence because it's
Yeah.
a dependent clause.
Sentences are a proper subset, or are a sentences are a proper subset of clauses. Yes. So we've talked about some kinds of phrases: noun phrases, prepositional phrases, sentences. It would be nice if we had a way of formalizing all of this, of representing this all in a mathematically well-founded way that we could then implement computationally, right? That would be much nicer than just talking about things informally. We would like that better, wouldn't we? Who would like that better? Apparently only some of us would like that better. Well, too bad. It's what you're going to get. So we're going to talk about context-free grammars. A great thing. Who invented context-free grammars? Chomsky worked with context-free grammars, but actually the earliest context-free grammar is found in the grammar of Panini, who's an Indian grammarian. Anybody here heard of Panini before? Anyway, yeah.
Sanskrit grammarian.
Yeah, Sanskrit grammarian, yeah. So basically a context-free grammar, not in Panini's formulation, but in ours, consists of the following elements. So we have a vocabulary of terminal symbols. So we call sigma. It's like the alphabet in phonics state transducer, except we probably think it means words. So this is a set of words. A set of non-terminal symbols. So these are like the names of phrases that are, which you could then rewrite or realize as words. You've got a special start symbol, which we write as S. You can think of that as being either start or sentence for the purposes of this class, but it really means start. And then you have production rules, where this means X, a non-terminal, is rewritten as alpha, which could be either a non-terminal or a terminal, or some string of terminals. It could be either, a string of non-terminals or terminals. Let's just see. So we call them context-free because there's only one thing on this side. On the left-hand side of the rule, there's just one symbol. So the rule applies without respect to what is coming before or after. So you rewrite why am I pointing at that? You rewrite the this symbol x as alpha, or you can rewrite it regardless of what is occurring before or after x. And that's what makes it context-free. So we'll talk later about grammars that are context-sensitive or context-dependent, where you might have context that exists on one side or the other or both sides of this symbol that restrict when you can rewrite the symbol. So this all probably seems somewhat abstract. Probably not. If you haven't dealt with context-free grammars before, it might not be immediately obvious how this relates to natural language or to the kinds of problems we want to solve. Yes?
I don't think there is just one symbol on the right-hand side.
On the left-hand side. I shouldn't have said.
I'm sorry.
I probably made the mistake, but it's on the left-hand side. There's just one symbol. I have trouble with left and right.
I'm having trouble.
So a non-terminal symbol, to explain how this works, is one like S. This can, and in fact must be rewritten as either other non-terminal symbols or as terminal symbols. So non-terminals can be either phrases or they can be what are called preterminals. Preterminals look like part of speech tags. So N for noun or P for preposition are often used as preterminals. In the terminals, if we're doing natural language syntax, are usually words or word-like tokens. And you can't rewrite the words. So you can't have a rule that says, like the arrow noun phrase or the arrow a. That's verboten. Because the is a terminal and you can't rewrite a terminal. You can only rewrite non-terminals. So once you've rewritten all of the non-terminals and everything is just a terminal, then you're done. The derivation is complete. And you have a sentence. And if your grammar was good, then it's a grammatical sentence. And if your grammar was poor, then you're fired. So here is an example of a context-free grammar. We used a little bit of a shorthand here. So this actually means determiner goes to the and determiner goes to a. And this means noun goes to boy and noun goes to girl and noun goes to hot dog and likewise. So I want you to tell me all of the sentences you can that this grammar will generate. So basically, we start off with S, and then we can rewrite NP as only determiner and noun, VP only as verb and NP. Then determiner can be rewritten as the or a, noun can be rewritten as boy, girl, or hot dogs, verb can be rewritten as likes, hates, eats. So I want you to list as many sentences as you can and find out which sentences are ungrammatical, what ungrammatical sentences this grammar generates. And I want you to start now. So what are some of the sentences that it generates? How many does it generate?
108.
108?
108.
108. I believe that's correct. Yes.
Well, I think you could have a sentence like a hot dogs.
A hot dogs. So that would be ungrammatical. An example of ungrammatical sentence that it generates. A hot dogs likes
A hot dogs.
boy. Likes a boy. Yes.
Is that sentence really ungrammatical? Because it makes sense, but semantically it is not meaningful.
It's semantically meaningful. It's fine if you say a hot dogs eats a boy, eats the boy. Then it's a little weird to say that a hot dog eats a boy, but it's conceivable. You can imagine a world in which we're surrounded by killer hot dogs. But it's not syntactically well formed because you can't have a hot dogs. That is, you can't have the indefinite article with a plural, so it's the indefinite article singular, hot dogs is plural. It's not okay. So any other interesting sentences that you generated?
Is there a way to tell if the person's name is hot dog?
It's capitalized.
Then
Just
is there
kidding.
a way to tell if someone actually omitted, say if someone made a typo,
Uh-huh.
he was supposed to say a hot dog, and
Uh-huh.
instead he said hot dog, then is there a way to tell if he made a typo or just a hot dog that refers to person?
I don't know of a really good way of doing that unless you have a broader discourse context. And then there are ways, if you can look at co-reference and can tie it back to a person. But just out of context, I don't think there is a way.
Okay.
So context-free grammars are kind of declarative programming. Who here has done declarative programming before? Program in Prolog, because you're from the earlier AI era, or SQL, SQL if you're a barbarian, XQuery, probably not. So these are all declarative programming languages where you, rather than telling the computer what it should do step by step, you're telling it what you want, what the constraints are in the case of Prolog or CFGs, and you're then leaving it to other algorithms to figure out how this is achieved. So with a CFG, it's not an algorithm for parsing a sentence or generating a sentence, but it's a way of describing how sentences could be parsed or generated, or provides a set of constraints for doing this, then can be used by any number of different algorithms for achieving these ends. This is also true of regular expressions or for finite state machines, right? They're not algorithms. They don't do stuff by themselves. They're descriptions of a solution that can then be taken and run by some, you can give them as input to some algorithm that then can use them to do what you want. But they're not a description of step by step what you do. they're a description of a kind of mathematical concept or constraint that then you can use in an algorithm that knows step by step what to do. So we'll learn about different parsing algorithms for context-free grammars. One of them that you'll be expected to know a lot about is called CYK or CKY. And this is a pretty simple algorithm that works with a subset of context-free grammars that are in what is called Chomsky normal form. It's a very nice algorithm. Not super efficient, but none of the parsing algorithms are super efficient. They're like worst case cubic time, which is sort of bad, but what are you going to do? I guess find a better algorithm. That's your job. But there are a number of different parsing algorithms that you could use. And you could basically feed a context-free grammar to any of these algorithms. It would be independent of the specific algorithm. So here's another example of a context-free grammar. This is a context-free grammar just for noun phrases. And it's somewhat more complicated than the noun phrase back here, right? Noun phrase here is just the determiner and a noun. But that doesn't really allow us to generate sentences where there are adjectives, right? So you can't say, this can't ever generate, the good boy likes hot dogs, likes the hot dogs. It can only generate the boy likes the hot dogs. So here is an example of a somewhat more complicated grammar for noun phrases that allows you to have adjectives, for example. And prepositional phrases. This I give you as an example because when you're doing your context-free grammar homework, you'll want to refer back to this because it will give you some idea of how you could implement noun phrases within the context of the exercise. And some general ideas about context-free grammars. One thing that people sometimes get confused about is they think, what is the right context-free grammar? What is the right context-free grammar for English? The correct context-free grammar for English. And this is not really a question you could answer. It's sort of like asking, what is the right way of implementing Levenshtein distance in Python? There are all sorts of different approaches that you could take that would give you roughly the right output, but they're going to have different performance characteristics and they're going to be differently maintainable. But really, it's going to vary depending on the task that you're interested in, what a good context-free grammar looks like. And in actual fact, we'll find that we'll make you write one by hand because, well, clearly because we don't like you. No, but that's not what people do. I mean, some people do. So like the grammar, if you ever use Microsoft Word, I don't recommend it, but if you do, there's the blue squiggle that does the grammar checking. That actually uses a hand-coded context-free grammar. But I don't recommend it. what people actually do is learn context-free grammars from tree banks. And they learn probabilistic context-free grammars, or PCFGs, from tree banks. And they the tree bank that you use really affects what domain the context-free grammar is applicable to. So if you train on a tree bank that's mostly news text, you do a lot better on news text than you would on like social media text. Because the patterns end up being subtly different, but different enough that it affects performance. And the words are totally different. So, that's something to be concerned about. I've been throwing around some terminology, and I want to clarify it now. I've said grammatical. I described a couple of sentences as grammatical and a couple as ungrammatical. By grammatical, I mean it's a sentence in the language. And this could mean two different things. Number one, it's a sentence in a human language. Or number two, it's a sentence in the language described by or defined by a context-free grammar. And if you think that human language capacity has something to do with context-free grammars, then these two things might overlap with each other, but otherwise they don't. In any case, ungrammatical we will use to mean a sentence that's not in the language. And derivation we'll use to mean a sequence of top-down production steps. So you start at S, you rewrite S as NP and VP, you rewrite NP as determiner noun and VP as VNP, and so on. That's a derivation. So it gets you from S to a bunch of terminals, to a sequence of terminals. And when we represent this as a tree, we call it a parse tree. So a string, according to these definitions, is grammatical if and only if there exists a derivation for it. So here's a parse tree. It shows, so if we were to do a derivation, we might start with S, rewrite S as NP and VP, rewrite NP as determiner noun, VP as VNP, rewrite noun phrase as determiner noun, then rewrite determiner as your, processes as noun, consumed as V, as the V is consumed, determiner as the, noun is memory. That's a derivation. We'll not go through this, but one thing that you'll find out is that sometimes you can have strings of terminals where you have the same terminals, but you have a different structure. And this is ambiguity. Sometimes this can be meaningful. So if you say something like, I saw the man with a telescope, it's going to mean two things, right? What are the two things it could mean? Yes. Yes.
You see the man using a telescope, or the man had a telescope.
I saw the man who had a telescope, or I saw the man using the telescope. Yeah. So those would have different parse trees. And we want to be able to capture the difference between those two parses of a sentence. On the other hand, there's what's called spurious ambiguity. And sometimes if we write our grammar badly, we can generate ambiguity that has no corresponding semantic difference. So it's just syntactically different, but there's no semantic difference. So there's a problem with grammaticality for humans. like if we're talking about human language capacity, and that's that it varies. So there's sociolinguistic variation in terms of what is acceptable grammatically, what is part of somebody's grammar. So if I say, I'll write the company, who likes I'll write the company? Who likes I'll write to the company? Yeah, so there's variation, actually regional variation about whether you say I'll write the company, I'll write to the company. In British English, I think the first one is more common. What about, okay, here's where we disclose if we, it needs to be washed. Who likes that? Who likes it needs washed? No Pittsburghers here? Yeah, so in some dialects of English, including Pittsburgh dialect, then people say it needs washed rather than it needs to be washed. And if you ever have contact with somebody who is from Pittsburgh, then you'll find this out. Yeah. Just a thought. What about they met Friday to discuss it? Okay. They met on Friday to discuss it? Yeah. So people's concept of what is grammatical, what is inside of people's heads as part of their language, varies particularly both regionally and according to things like social class and ethnicity. Basically according to identity. So people tend to talk like the people they identify with, and people who have different identities talk differently as markers of identity, and that means they have different grammars. So CFGs just basically provide you a mechanism, a tool for creating grammars. They could be good grammars that work well for your application or bad grammars that work poorly for your application. But there's nothing that tells you in the theory how to write a correct grammar or a good grammar. There are kind of general guidelines that you can follow, but that's not what the theory is about. It's mathematical formalism that you can then apply to these problems, but it's not in itself the solution to these problems. Well, what makes a grammar good? In a way, it's the same things that make a classifier good. What makes a good classifier? What do you like in a classifier? If you're choosing a classifier, what... Apparently, nobody's chosen a classifier. Anyway, you don't have strong feelings about classifiers? Yes.
You want it to do lots of things right and not a lot of things wrong?
Yes. You want to minimize false positives and minimize false negatives, right? That's the same thing with a good grammar. You want one that doesn't over-generate very much and doesn't under-generate very much. But what this looks like in a particular context is going to vary depending on your application space. So why are we building grammars? Well, we want to answer the question, who shot whom? Or who bit whom? If you don't like guns, but still like violence. So if we have the sentences, Oswald shot Kennedy, Kennedy was shot by Oswald, Oswald was shot by Ruby, then we can ask, who shot Kennedy? we've got, if we do the bag of words approach, we've got Kennedy, we search through there, we've got Oswald, we've got Ruby. Who shot Kennedy? The CIA. How do we know that Oswald shot Kennedy? I mean, you're trying to tell your computer. You're trying to get your computer to tell you who shot Kennedy. How do you tell it? Yes.
Exactly the same pattern as person.
Okay. So you just substitute. You find what would match who. How far would that get you? Is that a general principle, or is that just something that works in this particular case?
Only words for the person.
Yeah. Yeah. If we ask who shot Oswald, then we can't go through and say, okay. Dot star shot Oswald. Scan through the things. There's nowhere it says, well, who did shoot Oswald? Ruby. But there's no sentence that says Ruby shot Oswald. How would you possibly know that Ruby shot Oswald?
Because if you had a grammar that could parse it down to subject and object, then you could see that Kennedy is the object in the first sentence and Oswald is the subject. And so you can see that the relationship is that the action of shot is being directed toward Kennedy done by Oswald, and it would end up being the same thing for the last one.
So basically what you need to do, to put this in somewhat different terms, is you need to find what is subject and what is object. Subject, object, subject, object, subject, object. And then be able to map from subject and object to semantic roles, like agent and patient, where agent is the one who does the action and patient is the recipient of the action. And if you recognize syntactically that this is a passive sentence, then you know that the subject is likely to be a patient, and the object is the agent is likely to be in this prepositional phrase. And so you can then answer the question, who shot Oswald, by saying, okay, the agent Ruby shot the patient Oswald. So syntactic parsing is kind of a waypoint between text and answering this question, who shot who? So there are a lot of reasons, actually, that we want to build grammars, but this is an important one. We want to be able to do semantic role labeling. And we can't do semantic role labeling until we have syntactic structure, in some sense. We can't do these separately. You could learn them jointly, but you basically have to have both of these. Or you have to have syntactic structure in order to decide semantic roles, who did what to whom. So I'm going to talk a little bit about some myths about subject, because subjects and objects are important syntactic notions that we need to know about in order to understand how something like semantic role labeling would relate to syntax. So the first myth is that the subject is the first noun phrase in the sentence. The second myth is that the subject is the actor in the sentence, like the agent. And the third is that the subject is what the sentence is about, which seems to make sense. After all, it's the subject, right? So that must be what it's valid, right? But it's not. All of these are often true, but none of them is always true. And none of them tells you what a subject really is or how to use that concept. So who has heard one or more of these myths? Who believes one or more of these myths? And will, regardless of what I tell you. So subjects are syntactic, not semantic. So if I say the batter hit the ball, then the subject is a semantic agent. But if I say the ball was hit by the batter, the subject is the semantic patient. And if I say the ball was given a whack by the batter, the subject is a semantic recipient. Also, you can have different levels of agency, different levels of volition in subjects. So you can say George opened the door, and that's fine. George is volitional. He acts as an agent. I can also say the key opened the door. Well, the key is not really acting. The key is just an instrument that is used to open the door. And finally, I can say the wind opened the door. The wind does open the door, but it's not volitional. It's just a force. So semantic role doesn't line up with agent, but neither does the notion of topic. So if you say, I just married the most beautiful woman in the world, you could say that the topic is I. It's also the subject. But if I say, now beans I like, what is this sentence about? Is this a sentence about I? This is a sentence about beans. An important sentence about beans. And if you say, as for democracy, I think it's the best form of government, what is this sentence about? What is the topic, we say, in linguistic terminology? It's about democracy, isn't it? You're talking about democracy and making a comment about this topic. Well, what makes a subject a subject? In English, subjects agree with verbs. When the subjects are pronouns, then they're in nominative case, and they get omitted from infinitive clauses. So in I tried to read the book, or I hoped to be chosen, then you don't have a subject in that blank position. Objects, on the other hand, when you replace them with pronouns, then they're in accusative case. So like me, him, her, or him, as opposed to I, she, and he. And they become the subjects in passive sentences. So if you take a sentence and passivize it, then the object becomes the subject. Yes?
Could you go into a little more detail applying this to, I think it was the second sentence on the last slide? Yeah, the ball was hit by the batter.
Uh-huh.
Can you go into a little bit more detail about the ball versus the batter and identifying which is the subject?
So the ball is the subject. And the batter is neither the subject or the object. It's what's called an oblique. So this is a passive verb. So was hit is passive, and it only takes one argument, and that happens to be the subject. So this comes from this sentence. The batter hit the ball. Here, this is the subject, and this is the object. And when you passivize, when you make a passive form of a sentence, then the object becomes the subject. And the subject becomes an oblique.
Thanks.
No problem. So we've been looking at context-free grammars, but this is not the only way to look at syntax. In fact, in your projects, many of you will use dependency parsers. Who here has heard of a dependency parser before? What's a dependency parser?
So it tells you what the agent of an action is, or how a particular part of a sentence is related to a previous part.
Right. So it parses, rather than grouping things into a nested set of constituents, it relates individual words to other words in the sentence. So you get a kind of, this has a mistake in it. This should say root up here and have a arrow going down. Going down here. So just pretend. So the batter hit the ball. You have hit, the verb, which is kind of the center of the sentence. It's the head of the sentence, we say. And depending on it directly are a subject, which we describe as batter, and this is labeled dependency, so that's subject batter, and object ball. And then batter and ball both have dependence as well. So the depends on batter here, and this the depends on ball. So it's a modifier, or mod. So this is what a dependency parser gives you. This is what a constituency parser gives you, like from a context-free grammar. So you can see that the batter form a constituent, hit the ball forms a constituent, the ball forms a constituent. But here instead you see, oh, the subject of batter or of hit is batter. The object of hit is ball. This is another representation of the same information. Does that make sense? Do you see the kind of the difference between? So why would this be useful? What can you think of that would make a dependency parser useful to you?
You can answer questions based on this. So you can answer questions like who hit the ball, or who was the ball hit by.
Right. So if you have a way of mapping between relations like subject and things like semantic roles, then you can see immediately, oh, batter is the subject of hit. Ball is the object of hit. We can map those on to agent and patient and know who it was that hit the ball. So there's another thing. So if you're looking for relations in a text, in a corpus of text, then one way of stating these relations is as triples, right? Which is sometimes described with different terminology, different meaning of subject and object, but sometimes subject, predicate, object, or subject, relation, object. How would dependency parsing be useful for extracting this kind of relation? Yes.
So I guess one idea is it sort of narrows down what you need to search for in the text. Like in this case, you're maybe looking for verbs to start for, and then that can be, used as sort of the root input to parse.
Yeah. So your verb often is going to be the name of your relation, right? And the arguments of your verb the places in the relation are going to be dependents of the verb. So you can use this kind of parsing to extract that sort of information. And there are different, more or less sophisticated ways of doing it. But this is one thing that can be very helpful. And that could be helpful to you in your projects, depending on how you implement them. I mean, there are ways of doing it that are very just bag of words information retrieval-y, and there are ways that are a little bit more NLP-ish. And we don't want to prejudice you a priori in one way or the other, but you should know, there are a variety of different options. And so if we want to find subject and object, which kind of parse makes it easier? You can find subject and object in a constituency tree. The subject is here, daughter of sentence, or the start symbol. The object is here, daughter of a verb phrase. But what about dependency tree? How hard is it to find subject and object? Very easy. Why? Because they're labeled subject and object. So there are some advantages and disadvantages to these as syntactic representations, to constituency or phrase structure grammars, and to dependency grammars. For phrase structure grammars or constituency grammars, they're widely agreed upon tests for constituency, for what is a constituent. These require some skill to apply, but you can train linguists and annotators to do this pretty consistently, so you can get annotated data that reflects this. It also is good for some kinds of semantic representations. There are cleaner mappings for, like if you're doing a semantic representation stated in terms of first-order logic or lambda calculus, then there's a cleaner mapping between syntactic structure and that kind of structure when you're using a phrase structure grammar. For dependency grammars, they make it a lot easier to identify grammatical relations, things like subject and object. And it's also true that dependency parses of the same sentence often look more like, in a different language, will often look more like one another. So a dependency parse of English and a dependency parse of Russian are actually going to be more similar to one another if you look at the graph structure as opposed to the sequence of things than for constituency parses. For natural language understanding, then dependency parsing is also useful. This is what Google uses. And dependency trees are typically simpler, a little easier a little more tractable. Constituency sentences can be very heavy. Constituency trees, and dependencies are lighter weight. So there are approaches to syntax, including lexical functional grammar, or LFG, that use both dependency and constituency representations in parallel. Also, Stanford Parser, which many of you will use in your projects. Who here has heard of Stanford Parser before? The rest of you will hear, well, I guess you already have heard of it, but you will hear. So Stanford Parser is Stanford Core NLP tools are pretty good, and they're free and readily available and easy to understand, and there are good interfaces for them for various programming languages. But Stanford Parser can do both constituency parsing and dependency parsing, and that's nice. So you have that available as an option if you want to do. So there are other dependency parsers as well. So for example, there's a good dependency parser in Spacey for English. Who here is used Spacey? Anybody planning to use it in their projects? Yeah. Yeah. So if you use the dependency parser, you played with it. What do you think? It's got pretty good performance. But there are other parsers too, like Berkeley Parser, Malt Parser, SyntaxNet, and Parsey McParseface. Who here has heard of Parsey McParseface? What is it?
So it's the only thing, but it's like the name is based on the Bodie McBoatface.
Yes.
I don't remember the whole story, but it was like a boat that was crowdsourced to find the name for it.
Yes.
And, yeah, the internet chose Bodie McBoatface.
So Google, for the English model for SyntaxNet, they chose Parsey McParseface. Anyway. But it's and it's freely available. It's actually not that much better than the other options, but there are other things. So any questions? You think you've got a handle on this syntax thing? What about the preliminary reports? Any questions about that? Yes?
I think there's a point that says we need to identify nouns in a given file. Like
Yeah.
that file on the
I
website.
think it was posted on Piazza. Let me look into that and make sure that that was taken care of correctly. If you have a noun counter, then any file should be the same, but we'll get that to you soon if it hasn't already been posted. My recollection is that one of the TAs posted it on Piazza, and I don't want to post a different file if they've already posted something. But any other questions about that? Okay, let's go.